All right, everyone. Welcome back to Calculus 2. So I have some quick announcements before we get started. So because I wasn't able to make it on Friday, we missed finishing up improper integrals, and we also missed talking about techniques of integration, which was essentially just a review and sort of methodologies on picking which techniques to use when. I'm going to be posting a video about that sometime tomorrow. So sometime tomorrow, you should be able to watch that. And then I'll be posting the homework for that once I post that video, and you guys will have about a week to do that. But today's material, we're going to keep moving on, but today's material doesn't depend on the stuff that we missed on Friday. So don't worry about that if you haven't seen anything yet here. All right, so what is today's material? Today we're going to be talking about volumes of revolution. And technically, I think this is lesson 11. Okay, so there's two aspects to this phrase. There's volume and there's the revolution. So today we're going to just talk about how to find volumes in general using integration. And then the revolution will be coming this Wednesday. So that'll be what we're going to be doing then. All right, so let's just talk about volume. And I want to start off with kind of a basic example here. All right, so what I want you guys to do, what we're going to do, this isn't a practice problem. Find the volume of a square pyramid with base length of 20 meters and a height of 10 meters. Okay, so now the easiest way to do this problem is to go to Google and type in volume of pyramid with these dimensions, and it'll instantly spit out the formula, which is V is B squared H over 3. So if we use this, it's going to be 20 times 20 times 10 over 3. So it's going to be 4,000 over 3 meters cubed. Okay, so that's the easy answer. And you might think we're going to be done with this. Okay, well, we just looked something up, but where does that formula come from? Where does B squared H over 3 come from? How do we know that's really the volume? And what we're going to be doing is we're going to compute this in a much different way, and granted a much more difficult way. And we're going to effectively use the known formula to check our answer. And that's a technique I would recommend often when you're learning new math. If you're ever learning new math, or especially if you're learning a new way to do an old problem, do it the old easy way first as a way to check your answer for doing it the new way. So if we do it in our new way, we should get 4,000 over 3 as our answer here. Okay, now what's our new way? What are we going to do with this? Well, let me try to draw this pyramid here. So there's the square base, and then it goes up like that. All right, so there's our square pyramid, and each of these sides are 20, and then the height from the tip down to the bottom platform here is 10. And this definitely isn't drawn to scale. I think this height is longer than those, but you guys get the picture. All right, so we effectively want to find the volume of this. Now, what we're going to do is we're going to break up this pyramid into pieces. We're going to find the volume of each piece, and we're going to add it together. That's going to be our methodology here. Now, to make things simple and to not draw in 3D, you'll get enough of that in Calc 3, I'm going to just do the side view of this. So the side view of this pyramid would be where we have a base of 20 and then a height of 10 like this. All right, so this is the side view. Okay, so now what are we going to do now? Well, before I figure out the exact volume of this pyramid, I'm actually going to do an approximation. And I'm going to do an approximation by trying to match up rectangles with the pyramid. So I'm going to use 2 rectangles to do this at first. So my first rectangle is going to go halfway up the pyramid and then kind of cut across and come down here. And my second rectangle is going to go up the other half of the pyramid, but it's going to start and be a little bit smaller because the pyramid's thinner up here. Now, remember, this was a 3D object, so these technically aren't rectangles. You can almost imagine these as kind of rectangular cubes like this. So remember, these are 3D as well. So if we want to approximate the volume of this pyramid, what we can do is we can find the volume of each one of these cubes right here, or these prisms. So let's see here. So what's the volume of this big bottom one going to be? Well, this is 20. If it goes this way, it's also going to be 20. So we have 20 times 20. And then what's the height of this if it goes halfway up the pyramid? 5. So that's the volume of this big box down here. And then this smaller box up here, well, if we're halfway up the pyramid and the pyramid started with a width of 20, what do you think the width of this part's going to be if we go halfway up? It's going to be 10, right? So this time the base width and length here is going to be 10. And then what's the height of this going to be? Well, we already went up 5 meters, so we have to go up the remaining 5 meters. So it's going to be 5 again. All right, so if we multiply this out, let's see, 20 times 20 is 400, and then times 5 is 2,000. And then we have 10 times 10 times 5 is 500. So we end up getting 2,500 as our approximation for our volume, or the size of these two boxes. All right, well, is that a good approximation? Well, if we went up here and divided this 4,000 by 3, that'd be 1333.3 repeating. So no, this is an awful approximation of our pyramid. It's twice as big as what we want. Okay, well, that's not very great, but and we kind of see why that is, right? Like these boxes, they go over the edge of the pyramid, so they're getting too much volume that's kind of on the outside of the pyramid. So that's the reason why we're overestimating right here. All right, so let's see here. Well, if we want to have a better approximation, why don't we just use more rectangles? Let's see if that works. So let's use 5 rectangles now. Yeah, so we have an observation from the audience saying this kind of seems like something we did in Calc 1, where we were trying to compute areas in that case with a bunch of rectangles. And the more rectangles we had, the better it got. And that's not a coincidence. We're going to be using that relationship soon. All right, so let's say we have 5 this time. Okay, remember, this is just the side view. It's 2D here, but remember, all of these are actually volumes. You can almost imagine this rather than like an Egyptian pyramid, you can almost imagine this like a Central American pyramid, for example. All right, so we need to find the volumes of each one of these. Now remember, the base length is going to be 20, and then the height is going to be 10. All right, let's see. So the base length is 20 this time. So again, we have our 20 times 20. But then what's the thickness of this if we divide it up into 5 pieces right here? It's going to be 2. Okay, now if let me ask you this. If we go 1/5 of the way up the pyramid, we're going to lose 1/5 of our length for the base, right? Because our triangle is getting shorter or thinner as we go up there. So what are the numbers I'm going to square next? 16, right. Remember, we start at 20 and we need to divide it into 5 pieces because we're going to lose 1/5 of it each time. 1/5 of 20 is 4, so we're going to go down by 4 each time. So you have 16 times 16 times 2, that's going to be the second one. And then the pattern continues as we move up. So we have 12 times 12 times 2, 8 times 8 times 2, and then finally the little box on the top will be 4 times 4 times 2, like that. Okay, and to save time, I added all of this up in advance. So this is 800 plus 512 plus 288 plus 128 plus 32, and that adds up to be 1760. All right, now is this a good approximation for the size of the pyramid? Well, it's certainly not as bad as the previous one is here. It's not double the size. And it's getting closer to that 1333 that we know it's going to be, but it's not quite there yet. And what's a way we can make it better? Well, we can have more rectangles. I'm not going to bore you drawing out 10 rectangles or 20 or however many, but I think it's pretty clear that the more rectangles you have, the less we're going to overestimate the value of this pyramid, because there's going to be less kind of going over the side like this right here. So why don't we just have as many of these rectangles as possible? Why don't we send the number of rectangles to infinity and make them as thin as we possibly can? And that's exactly what we're going to do. We're effectively going to take our pyramid and divide it up into these little infinitely thin slices. They look like this. And remember, these are still 3D. I'm just drawing this for 2D for simplicity, but remember, these are technically 3D. So if you want to think about this as similar to a physical object, this is kind of like a CD case. It's like super thin, but it's still a rectangular prism right here. Okay, now let's see here. If we want to add all of these up, we need a formula for how big they are, right? So I'm going to call each one of these a slice. It's almost like we're kind of taking a very thin slice out of the pyramid. So what's the volume of each one of these slices? Well, the volume of a rectangular prism is the length times the width times the height, right? Now, the height, I'm going to define a variable h, where h is how far from the top we're going to be. Now, if we ever have a very tiny change in a variable, there's a special way of writing that, right? Does anyone remember the way, like if this is the h direction, what is this little tiny height going to be called? Yeah, delta h, specifically, we're going to use dh. Delta is for like any kind of change. Dh specifically means a small change. So we're going to use dh for this. So since that's our height, we have length times width, and then our height is really dh because it's super tiny right here. All right, how is there an infinite number instead of just a large number of finite numbers? That's where the limit comes in. Yeah, we can't actually have infinitely many, but we can see what the trend is as we head towards infinitely many. So we're going to have a limit coming up. All right, next we need to have the length and the width. Now this is a square, right? It's a square pyramid, so these are actually the same. So it's really just going to be the width squared times dh. All right, and then the width is this right here. Now, what I'm going to do, let me kind of spoil what's going to happen here. Whenever you add up infinitely many tiny things together in this manner, it's going to form an integral, because what we're doing is we're computing what's called a Riemann sum. Now, when we do an integral, I'm going to slap it in. Let's pretend we like slap an integral sign here right now. What's the problem with this integral? Well, we're doing the integral with respect to h, but we have w as a variable. And we don't necessarily know immediately how w depends on h. So we can't do this integral right away. So what we need to do is we need to change this w into h's, meaning we need a relationship between w and h. Now, for each one of these problems, this relationship is going to be different each time. And for this problem, we're going to exploit some geometry here. So notice that we kind of make this little mini triangle, right? So we have this kind of smaller triangle up here where it comes h down from the top and then it's w wide. Now notice that just looks like a smaller version of the overall triangle. And there's a special name for when triangles look the same. It's just one's bigger or smaller than the other. Does anyone remember the name for that relationship? Yeah, they're going to be similar triangles. That's right. So this smaller triangle here is said to be similar to this triangle right here. Okay, now what does that mean mathematically? It means that the ratio of their side lengths is the same. So if I do the vertical dimension divided by the horizontal dimension, that's got to be the same as the vertical dimension here divided by the horizontal here. So the vertical dimension for the entire pyramid is 10, and the horizontal one is going to be 20 right here. All right, so that means that our h is 10, our width is 20. Now that's really nice because then I can cross multiply here. So 20h is 10w, or 2h is w, right there. All right, now that's really nice because now I have my relationship between w and h. So what I can do here is if I want to know the volume of each slice, remember we now know it's w squared dh, but now I could put this formula in there. So I get 4h squared dh. And remember, we get a 4 because we square that 2 as well. All right, so there we go. We have a formula for the slice depending on how far down from the top we are. If we're h down from the top, this is going to be the volume of our slice. Now, of course, we don't want the volume of just one slice. We want the volume of all of the slices. And when we add all of those tiny slices together, so when their powers combine, all slices, this turns into an integral. So the integral, our total volume, V total, is going to be the integral of 4h squared dh. Now, this is always going to be a definite integral. So when we're at h equals 0, we're at the very tip of the pyramid, right? We're not down from the top of the pyramid at all. So we're going to start at 0. And then what's going to be the upper bound for this integral? How far down can we go from the top of the pyramid? 10, right? All right, so this integral is going to give us the volume of our pyramid right here. All right, and then this actually isn't too bad of an integral. So we did this at the end of our integration section, so you may expect, okay, we're going to pull out all the stops, do a bunch of trig sub and everything, but no, this is just something we could have done in Calc 1. So we do the integral of this, and we get 4h cubed over 3 from 0 to 10. So I put 10 in there, and I put 0 in there, but that will just be 0. And then we have 10 cubed is 1,000 times 4, and we get that 4,000 over 3 that we were promised earlier. So this is where that formula comes from effectively. You can break up your shape into a bunch of slices and then integrate them to get your volume. Now, why did I waste our time doing this? Because we have a perfectly nice formula for this. I mean, it's not a mystery what that is. You can just go on Google and figure out what it is. Well, unfortunately, not all shapes are common enough that you can just go on Google and search for a volume for them. So if we have some very odd looking shape and there's not a common volume formula for it, we can probably do this instead and actually get there when we can't just look up the answer. But we like to start with easier ones so we can check our work like this. All right, so now I want you guys to give this a shot. And don't worry, this example is going to be extremely similar to the previous one. There's just going to be one difference here. So let's go on to the practice problem, and this is something we'll do on campus here. Okay. Find the volume of a cone with height 20 meters and radius 10 meters. So I want you guys to do that. And obviously you can look it up. You can go on there and see that, oh, hey, the volume of a cone is pi r squared h over 3, and then just punch it in. But what I really want you guys to do is I want you guys to try to use this methodology up here. And you don't need to do like the whole drawing a few rectangles in a lot. You can kind of just like start right here if you want to. And I would recommend that. But yeah, I want you to kind of use the same kind of reasoning that we used in the previous problem to do this. And now there's only one difference between the previous problem and this one. In the previous problem, we had a triangular shape, and then the bottom was a square. But in this problem, we're having a triangular shape, but then the bottom is a circle instead. That's going to be our only difference between the two examples. All right, so I'll give you guys a few minutes to work on this. Yeah, so what the audience says is that our cross section shouldn't be a rectangle, it should be a circle instead. And that's an excellent idea. The radius is 10. Oh yeah, my one's a little squiggly. There we go, 10. And don't worry, we'll do this once we're finished. Once I give you guys a few minutes here. What time can we start our exam next week? It's going to be 8 to 10 p.m. for everybody. As much as I'd like to have it be open all day, I think that the university doesn't like that because it makes it easier to cheat. It's gonna be 8. Don't worry, I'll talk more about the exam next week. Don't worry about that now. How do we get r squared to h? I recommend taking a look at what we did right here. Remember, this is also a triangular shape, except it's just circles down here instead of boxes. So we can still use similar triangles to help us. Yeah, so how do we get a relationship between R and H? I recommend making a similar triangle like this. So H will still be exactly the same. We'll have H kind of come down from the top, but instead of W going all the way across, we're just going to have R go halfway across. And we'll do similar triangles with that. Eight thousand pi over 12, that sounds good to me. That simplifies a little bit to 2,000 pi over 3. All right, give you guys maybe one more minute here and then we'll start going over. All righty, let's take a look at this. So we know that our total height here is 20, and our radius is 10, right? Now this time, rather than breaking things up into rectangular slices like before, when we look at our side view here, and then we have our height down here, and then this halfway across is going to be our radius. And what we kind of imagine here is we have these discs. They're very, very thin discs. You'd almost imagine them kind of like a pile of coins, and the coins are getting progressively smaller as you go towards the top. And we're sort of stacking these coins, and the thinner that they are, the more accurate approximation will be. So ideally, we want to make them infinitely thin and have a bunch of them. Now, we need to get a formula for the volume of these, I'm going to call them coins. So the volume of this is technically a really thin cylinder, right? We have a circle and then it's moved by a tiny amount of height. So we have the area of a circle, which is pi r squared. And then what do you think I'm going to call the thickness of each one of these coins? dH, right. Whatever direction we're going in, if we have a tiny amount of change in that direction, that's always d and then whatever the variable is. So this is dH. Now remember, the whole point of doing this is so we can do an integral, right? Is when we add up a bunch of tiny things, that's the same thing as doing an integral. But the problem is that I have an r here and an h there. So I need to convert all of these r's into h's before I can actually do the integral right here. All right, so let's see here. So I'm going to use the same thing that I used last time. I'm going to use similar triangles. So I have this kind of smaller triangle up here, but then I can imagine that I also have a really big triangle that fills up the whole cone. And these triangles are also going to be similar triangles. If you can wedge in a smaller triangle and the sides are coincidental like that, then they're going to be similar triangles. So that means that if I divide h by r, I divide the vertical by the horizontal here, I'm going to get the same as if I divided the whole height by the whole radius. And the whole height was 20, and then the radius was 10. Okay, now I want to get r as a function of h. So again, I'm going to cross multiply here. H is going, or 10h is going to be 20r. And I divide by 20, h over 2 is going to be r right here. All right, so I'm going to take that, I'm going to substitute it into here. So then I have pi h squared over 4 dh. And again, I get this 4 because I squared this whole thing right here. All right, so now if I want to get the volume of all of my cone, I'm just going to put this into an integral. So I have pi over 4h squared dh. Okay, now this is something that can be kind of tricky. Maybe not for these first few problems, but it definitely will be for problems that we're going to have later on. And that's figuring out what the bounds are. And remember, the bounds, whenever we're doing a volume problem or maybe some kind of physics problem like we're going to be doing later, we always want to go over, have our bounds be wherever the object is. So that's one thing I really want to emphasize now. The bounds are wherever the object is. This is the key way to think about bounds when we're doing this integral right here. How'd the 4 get under the pi? It was pi times h squared over 4, so you can move the denominator fractions however you want. All right, so let's think about this. So h equals 0, that's going to be the very tip of our cone. So we're going to start there. And then we can go up to 20 down from the top. That's going to hit the base here. So our integral is going to be from 0 to 20 in this case. All right, let's go ahead and do this. So I do the power rule, raise this to 3 and divide by 3. And I have 0 to 20. And then I plug in 20. 20 cubed is 8,000. And then this will simplify to 2,000 pi over 3. And if I'm not mistaken, I think this is the answer you're going to see in Canvas right here. All right, so yeah, so we were able to do the same thing again, only we did it with cones. And you could do this with pretty much any common three-dimensional shape you want. You could break it into little chunks or cross sections. If you add them all together, you're going to get the volume of the entire thing. All right, now both of these examples, though, have been for shapes that we already know the volume for. So why don't we try something that's a little bit less familiar, something we can't just immediately Google and figure out what the answer is. Because this was another thing we could have just immediately Googled. All right, let's move on to the next problem here. Sample 2. All right, find the volume of a shape whose base is the region.
Let me back up. Let me back up. Let me back up. Let me back up. I got you.
There we go. Whose base is the region between the x-axis and the parabola y equals 4 minus x squared. And whose cross sections, oh, almost looks like Crocs, cross sections perpendicular to the x-axis are squares. Ooh, baby, that was a mouthful. All right, so let's dissect this and see what's going on with all this. So first of all, we need to find a volume. Okay, so we're going to do it kind of in the same way that we've been doing this before. And now we want the base of this, so the bottom of the shape, kind of like the circle here, the square here, we want this to be something specific. And we want it to be the region between the x-axis and the parabola y equals 4 minus x squared. Now, one thing I'm really going to emphasize here, and this is very important, you need to draw the pictures for these. So the first step for all of these is to draw a picture. It's very difficult to do these problems if you do not draw a picture. So I highly recommend that you do that. So let's draw a picture of what the base looks like. So we have our axes right here. The x-axis is the horizontal axis. So that's this right here. I'm going to shade it in a little more. And then we have the parabola 4 minus x squared. Now there's a negative in front of the x squared, so that means it's going to be a frowny face parabola. And then we shift it up by 4. So we're going to have it be here at 4, and then it's going to kind of go down like this. Now we wanted the area in between. So that's going to be all of the stuff inside here. Okay, now that's going to be the base. It's almost like we're looking top down onto this shape, and this is what the bottom is going to look like. Kind of like if we look top down onto a cone, it'd be a circle. If we look top down into a pyramid, it'd be a square. It's going to be, this time it's going to be this weird parabola thing. All right, now let's look at the next part. And we want to see where the cross sections are perpendicular to the x-axis. So what that means, essentially what all of this is saying, is that we're going to integrate with respect to x. This is a common abbreviation, WRT, with respect to. This means that the integral, the variable in our integral will be an x. Now, if I said the cross section is perpendicular to the y-axis, then we would have dy as what we're doing here. All right, and then finally, we're going to get squares right here. So let's think back to the previous examples we just did. So with the pyramid, we effectively had the area of a square then times dh. With the cone, we effectively had the area of a circle, and then that was times dh. With this one, we're effectively going to have the area of a square, and that's going to be times dx. So that's kind of how we decipher what each of these is going to be. So what does this look like physically? Like if I were to draw the picture here, what is this going to be? Well, let's say I take a slice, and I take a slice in the x direction. So I have this tiny little slice here, and that's going to be dx. Now, remember, this is a 3D shape, right? This has volume. This isn't just area, this is volume. So how is this going to look three-dimensionally? Well, I said that each of these are a square, right? So we can imagine that this is the length of one of the squares, and then kind of popping out of the page here will also be a height L because it's a square. And then we kind of thicken it a little bit by dragging it along dx right here. So our cross-section shape is a square, and then the thickness of it will be dx. That's how we interpret these problems right here. All right, so that's what we're trying to figure out. So now we need to actually do it. Now we need to actually get our volume here. So first of all, I'm going to call each of these a slice. Slice is my usual name. Sometimes I also refer to them as chunks. We're pretty much going to do the same thing. We're going to figure out the volume of one of them in general, and then we're just going to throw that formula into an integral. Yeah, that's right. Yeah, Evan has the right picture here. So effectively, every time we do this problem, we're setting up a Riemann sum, and then we turn it into an integral. We don't need to write like the sigma notation for the Riemann sum, but yeah, that's what we're doing every single time. All right, so let's see here. What's the volume of each one of these slices? Well, let's see. So it's going to be the width times the height here. It's going to be L squared. And then the thickness of this will be dx right here, because this is the area of a square. And then this is cross section in the x direction. All right, so now what we want to do is we want to get L, or this vertical length right here, we want to get that in terms of x, because remember, that's our perennial problem with these types of things, is that this variable almost never matches this variable immediately. So we need to find some kind of conversion where we change all of these L's into x's. All right, so let's see. So I decided to call this L here, but what's another good variable name representing the length from the axis up to the function? Oh, what was that? Y, that's right. Yeah. So another name for L, a more conventional name, would be Y. Anytime you want to measure vertical distance from an axis, you use Y. So rather than have L squared as this, I'm going to have Y squared dx. That's the same thing. The distance from the axis all the way up to your curve, that's going to be Y. All right, now the nice thing is that we don't even need to use any similar triangles or geometry or anything like that. We actually just have an algebraic equation relating y and x. So we know that y is 4 minus x squared. So y squared will be 4 minus x squared squared. And there we go. So we have the volume of one of our slices, and now all of the variables are consistent. So we can throw it into an integral. So the total volume of our shape, which I think will look kind of almost like a wedge, like it's going to get taller and thicker as we go out, and then it's going to get thinner and smaller as we go in. So we're going to have the integral 4 minus x squared squared dx. All right, now what are the bounds of this integral going to be? When does the parabola 4 minus x squared meet the x-axis? When does that happen? Yeah, the x-intercepts, those will be, let's see, looks like we're getting plus or minus 2. That's right. So we're going to have negative 2 this way and then positive 2 this way. And that's where our parabola meets y equals 0, the x-axis. So this will be from negative 2 to 2. Now, here's one technique we're going to be using a lot more later in the class, but I figured I would introduce it now. So would you guys agree that the right half of this shape is going to be the same size as the left half? Does that seem feasible? Oh, yeah. What's your question? Oh, right. Yeah. So the height from here to here, this vertical distance, yeah, it is the function. That's why I just plugged it in right there. Now, depending on the problem, it may not be that. We may want to measure a different thing, kind of like how we measured the radius here and then the whole length there. So sometimes it might be different, but for this one, yeah, it's just a function. Why do we use negative 2 and 2 again? Because that, remember, we always want to have the bounds be wherever the object is. And the object starts right here when we're beginning to be under the dome of this parabola, but above the axis, and then it stops right here. And we get those by setting this equal to y equals 0, which is the x-axis. Now, there's something we could do here. We notice that the left half, it looks exactly the same as the right half. And these squares aren't going to change size depending on which side we're on. So one thing we can do is we could use symmetry to make our bounds nicer. So this is actually going to be 2 times the integral from 0 to 2 of 4 minus x squared squared. Reason being is that this is exactly the same size as this. So if we just count this one twice, then we'll still have the whole thing right here. If it were integration with respect to y, would we use 0 and 4 as the bounds? Absolutely. And in fact, you predicted an example that's coming later. We're going to use the same thing, but we're going to do dy. So yeah, keep that in mind for later. All right, let's see. How much time do we have here? Okay, so in the interest of time, I'm going to leave this integral to you guys to finish because this is a polynomial integral. We could square that out, do the power rule for each one, and then we would be done with it. So I'm going to trust that you guys know how to like compute that. It's really setting up the integral, which is what we're trying to do here. So in this, what we did in this inequality is we're using symmetry. So since this is the same size on the left as it is on the right, we're effectively just measuring the right twice, and that'll account for the left. All right. So with that done, I want you guys to practice doing this. All right. So I want you guys to do a similar problem. All right. Find the volume of a shape whose base is the unit circle and whose cross sections perpendicular to the x-axis are semicircles. So remember, the formula for the area of a semicircle is simply 1/2 the area for the regular circles. All right, so I want you to find the volume of this thing. And as a hint, I'll give you a hint for this one. You have seen this shape. This actually is a familiar shape, but it's kind of defined in this weird way. But you can use the same process that we just did in example 2 to figure out what's going on. Let's see, is this shape in this room? Like I Spy or something? I actually don't, no, I see it, I see it. Yeah, I see it. There's a few places, okay. Seeing it in the room is not gonna help you to do the problem though. Oh my God. Nice job, Kate. All right, now I don't want to be a killjoy, but I've happened to notice a correlation between when we're doing something that takes a long time or is complicated to when people start to like bring out pets or like talk about something else. And like I'm okay if you guys talk about like whatever in here, as long as it's like, you know, not offensive or hurting anyone's feelings or anything. But I would encourage you guys not to zone out when we're doing something hard. Like if something gets hard, you don't know what's going on, don't zone out. Try to go to where you last understood it and try to catch back up. I know it's hard to do that, and I know it honestly kind of sucks to do that, but it's really going to help you do better. Whenever this says perpendicular to the whatever axis, you're going to be your slices are going to be very thin in that direction. So we have very thin slices in the x direction here. We're going to have the same thing here. So we had these very thin squares here, right? So in this one, we're going to have very thin semicircles going horizontally across the shape. Okay, it's not a big deal. Don't worry about it. I was just kind of saying in general. I wasn't targeting you or anything. Yeah, what's up? Well, what do you think the shape is? Well, no, the unit circle is just literally like the circle, and then you have these semicircles kind of going across the top of it. All right, yeah, we'll don't worry, we'll go over in a second. Yeah. Yeah, the radius is a little bit different from just the length. We'll talk about that in a second. You guys try to draw a picture? Draw a picture. Okay. Yeah, make sure you draw a picture. A semisphere. No, hemisphere is the correct term. I don't think semisphere. Yeah, I don't think that's a technical term. I would know what you mean if you said that, but all right, the last 5 minutes here, let's go over this problem and see how we do it. So find the volume of a shape. So remember, let's try to dissect this again. So find the volume of shape whose base is the unit circle. So whatever the first thing they say is whoever the base is, we draw that picture. So we're going to draw a picture of the unit circle. Okay, so there's our unit circle, has a radius of 1. Okay, and whose cross sections perpendicular to the x-axis are going to be semicircles. All right, so what does that mean? So remember, when we're perpendicular to the whatever axis, that's going to be the variable we're going to integrate with. So we're going to have a semicircle kind of like this, and we're going to be very thin in the dx direction. Now, we always draw rectangles to start off with. When we're still in 2D mode, like we are right now, we always kind of draw a rectangle reaching from the bottom of the shape to the top of the shape. Now, whatever this shape is here, this comes in next. Whatever this shape is, this is going to be the 3D part of the graph. So kind of, you can imagine like above the circle right here, what's going on is that there's a semicircle kind of popping up out of the page and kind of going along here. You can almost imagine this picture isn't very good. You can almost imagine it as like a quarter that you put halfway into a vending machine slot. That would be a good way of thinking about this shape here. And the further you go towards the middle, the bigger this coin's going to be. And then as we get towards the end, it's not going to be very big at all. Okay, so this is the picture here. So now we need to know the volume of each one of these slices. And if we add all of those together, we're going to get the volume of the whole thing right here. All right, so let's see. The volume of a slice. Well, remember, the volume is always going to be the shape's area times d whatever it is. So we know we're at dx here, so we're going to have dx. And then what is the what is the area of a semicircle? What's the formula for that? Yeah, pi r squared over 2. Because pi r squared is for a circle, pi r squared over 2 is for a semicircle right here. So remember, this is a semicircle. Okay, and then this is the thickness right there. Okay, now of course we don't have r as part of our equation here. Actually, what is the equation for the unit circle? We didn't write that down. The unit circle has equation x squared plus y squared is 1. All right, so now let me ask you guys this. This is the radius of our semicircle, right? What's another name for r here? Y, that's right. Remember, whenever we have a height going from the axis vertically to our curve, it's going to be y. So this is going to be pi y squared over 2 dx right here. Okay, now once again, we have the same problem that we've been having for every single one of these. We have a y here and an x here, so we want to convert this into x's. We always want to convert this into this variable. We never want to try to convert this over here. We actually probably could do that if we did maybe the implicit derivative of this, but let's not do that. All right, so I see a y squared here and a y squared here, right? So I'm going to subtract x squared over. Y squared is 1 minus x squared. So this is pi times 1 minus x squared dx over 2. And there we go. Now everything's in harmony because we have all the same variables everywhere and then some constants here. All right, so now that we found the volume of one slice, the total volume is going to be an integral. It's going to be an integral of this exact thing right here. So pi over 2, 1 minus x squared dx. Okay, now here comes the question that we need to ask ourselves before we do this integral. What are the bounds for this going to be? Yeah, -1 to 1, absolutely. So where does our shape begin? Our shape begins over here, right? And on the unit circle, this is an x value of -1. And then we keep going, we have the bigger coins and then the smaller coins. And then we get over here and our shape is now over. And that happens at x equals 1. You always do it in terms of whatever this variable is. So you put the lowest number where the shape appears in this variable, and you put the highest number where the shape appears in this variable. And finally, yeah, so I was about to say this, yeah, the chat has it. We can use symmetry to make this a bit easier. So I think it's pretty clear that when we make this shape kind of coming from the left, it's going to be the same size as it is going down to the right. If that's not obvious to you, just don't worry about it. You could do this integral right here and it'd be totally fine. I just like to do symmetry because sometimes it makes the integral easy. So I'm going to double this and then only integrate over half of it. So like 0 to 1. And that's actually pretty nice in this case because those cancel out. All right, and then now I'm just back in polynomial world, which is a nice world to be in. I'm going to pull my constant pi out and do the power rule. So I have x minus x cubed over 3. This goes from 0 to 1. And then I plug 1 into here. 1 minus 1/3. So this is going to be 2 pi over 3 right here. So there's going to be our volume. And this makes sense, right? So does anyone happen to know the volume formula for just a sphere? What's the volume of like a full sphere? Yeah, 4/3 pi r cubed, right? So for a hemisphere like this, where we have semicircles, only half circles going here, it makes sense that if we have radius 1, we're going to have half of 4 pi over 3, so 2 pi over 3. All right, so there we go. So we got 2 pi over 3 for that one. Unfortunately, we are out of time, and there's one more example that I had where we did something perpendicular to the y-axis. I will post that those notes online. To tell you the truth, it's not really that much different from the x one. You're just effectively just using a different variable here. Then we multiplied by 2. We already multiplied by 2 here for symmetry. All right, guys, we will be doing more volume stuff next time. So I will see you all on Wednesday.